Awesome. Welcome, friends. This is another fun session with Deep Learning Adventures, a fun, engaging community where we cover deep learning, machine learning, and data science in general with friends all around the country and around the world. I'm joined by my great friends and co-hosts Robert and David, and my great friend Dmitri today. He's going to present our third session on transformers, specifically an application of transformers for non-NLP tasks. So welcome, everyone. If you're watching us from YouTube, thanks again for enjoying our sessions. Yeah, feel free to leave your comments, like and subscribe, and hope to see you in one of our upcoming sessions. Let me share my screen real quick. So you'll find us on Meetup. This is the third session, as I mentioned. It was an actual competition, as you'll hear from Dmitri soon, about a year ago regarding knowledge tracing. So you'll hear more about that and some innovative approaches that I find this a really interesting competition, and yeah, looking forward to taking a deeper dive. Just for you who are interested in learning more about our community, we have a few more upcoming events. We're going to switch gears after this session. We're going to talk a little bit about certifications next couple of weeks. Robert, Alana, and I are going to cover this cloud practitioner exam. How do you prepare for it, and what was our exam experience? And then after that, we're going to tackle what is called the AWS machine learning specialty. It's a specialization or specific exam in their curriculum. Cool. With that said, let me stop sharing and let's get ready for an action-packed session with Dmitri.
Okay, thanks, George. So let me share my screen. Could you enable participant sharing?
Yep. Sorry, I just enabled it.
Okay, there we go. Can you see my screen?
Yes.
Okay. So let me. Sorry about that. Okay, there we go. All right, so this is the third session on transformers, and we're going to be covering the Kaggle competition put together by this company named Riiid. So I was going to talk a little bit about the company itself, and then we're going to cover the Kaggle competition, the structure of the data set, and the requirements. And then we'll switch gears and talk about the transformers as they are applied both by the company itself, which turns out, uses transformers internally to predict how students gain knowledge, and also in the Kaggle competition. As far as I can tell, many winning solutions in the top 100 use transformers. And so we're going to discuss a few structures and then go through my specific submission. So that's the plan. Let me first just very briefly talk about the company. Let me make this a little larger. So the company is a South Korean startup, and they developed an AI app that prepares students to take the TOEIC test. TOEIC is an international English proficiency test, which is apparently favored quite extensively in Japan, South Korea, so in that part of the world.
Dmitri, sorry to interrupt. Are you intending to show something other than the notebook right now?
Oh yeah. Okay.
Right now we just see the collab.
Let me. Thanks, Robert. Can you see it now? Okay. Yeah.
Yeah, we see slides now.
Yeah, there was some Zoom hiccup. So the TOEIC test is an English proficiency test, and millions of people take it every year. And so this app was specifically built to help students pass it faster and better. And apparently that then affected, the chances of getting hired to big corporations in Korea and so forth. So this is a really, this turned to be a really useful app. Now, Riiid was founded and continues to be built around this idea of automatically tracking how the student develops his or her knowledge or proficiency in English, and then feed them the appropriate lectures and test them with appropriate questions, so level appropriate questions, so that they have the best chances to pass the test. So, you know, build and then construct the learning path in the optimal way. That's the overarching goal of this app. Now, they have a few videos. I included a few videos in case you want to check them out. Basically how they present themselves and also how they apply the AI. The second link is a very interesting AI talk given by their head of research, who discusses specifically how the machine learning and transformers are applied for knowledge tracing. And so if you have time, I highly encourage to watch them. Also, it's not ruled out that they will repeat the competition, because the data set is growing, and the app, you know, I think they just recently got a new round of financing. So this is a growing company. So this might be interesting. Now, just a few words about the Kaggle competition itself. This is also the link, and we will visit the Kaggle page. But basically, in a nutshell, this is how they present it. The overall goal is to build algorithms that track, you know, the development of the knowledge, and this is called knowledge tracing. But for the Kaggle purposes, the ML task is to predict how a particular student will answer a particular question, given the entire history of what they saw in terms of questions, which lectures they listened, how they answered the previous questions, what was the question difficulty level, etc., etc. So given all the information that is available up to time t, and then given the current question, predict with a, you know, with the appropriate probability. And so this is a binary classification task in itself. It's just that the features are temporal and could be complex. And so this is basically a time series based binary classification problem evaluated by area under the curve. Yeah, so a few words about the data set and some engineering challenges that come with the data set. This is called EdNet, by the way. They claim to be the largest educational data set that there is. It keeps growing. Now I think they have 300 million interactions. And interaction is basically each event that the student has on the app, which could be, you know, the lecture listened or, you know, question answered. It's all counted as interactions. This particular data set was covering 3 years of student interactions, you know, almost 400,000 students. And the data set, so the questions database is 13,500 distinct questions. 2/3 of which are generally answered correctly. I think that they spent quite some time, and they discuss it, preparing the data set for the Kaggle competition. They made it very clean, very homogeneous. There are no weird, you know, shifts or any kind of regime changes in the data, which are, you know, you encounter that all the time in the time series. No missing data, and so very nice, clean data set to work with. So regarding engineering challenges, so the data set itself is, you know, quite massive if you don't compress it. So we have to do things like converting to a specific data type, and then cutting some of the unused columns, etc. So the task of actually fitting and training, even on Colab, on a single GPU, not a GPU cluster, it was not a trivial task. So we had to go and find all kinds of ways to do that. So in the Kaggle competition, many teams actually used sophisticated GPU clusters, and they had special people taking care of the engineering side of the things. And in this case, it proved to be sometimes a competitive advantage. So those that had the ability to use much of the compute power and much of the basically people power, they tend to perform better. So one interesting feature,
Can I
or
ask a
the most,
question
sure, yeah.
on the data set itself? So when you mentioned that this is a binary classification, is there any benefit? Like I see most submissions, you actually submit a probability that the user will answer the question correctly. So it's a number between 0 and 1. Is there any value to converting that to 0 or 1 based on like a 0.5 threshold, or would you get different score if you submit it as a, let's say, raw number as a float between 0 and 1?
That's a good question. I don't know the answer to that.
I'm not sure if I understood the question exactly, but it looks like on your slide here it says it's being evaluated by area under the curve, which I'm assuming that's a ROC curve, or so in that case you would definitely need to submit confidence values in order to generate that ROC curve to rank the questions in order.
Yeah, I just put in the chat. So ROC curve between the predicted probability and the observed target.
And the observed target, yeah.
Yeah, so in that case, then you need to submit confidence values, some way of ranking your confidence on the questions.
So let's say my confidence is 0.9. Would my score be different if it was 1 versus 0.9?
It only matters the rank order.
Oh, okay.
But if you're submitting just binary classifications, then you really can only you can't say how confident that you were more confident in this yes versus that yes.
Okay.
All right, then. So as I mentioned, the company uses transformers itself, and this was one of the reasons I was interested in this competition in the first place, because at that time I was getting into transformers, exploring different architectures, etc. And then when I saw they mentioned this research in the Kaggle competition itself, so it was an interesting application of the transformers for non-NLP tasks. So I thought it would be interesting to explore. And so I was gonna spend just a few minutes going through this architecture because I implemented something very similar. I just basically copied this and then tried to modify it a few pieces. And many other participants, as far as I can tell, just also basically use this as a baseline. So what they do is basically apply the classical encoder-decoder architecture, and for the encoder part, they take the questions. So this encoder part is on the left. The exercise ID is actually the identity of the question that we're trying to answer. Positional embeddings and part embeddings that relates to which TOEIC test part that question comes from. This is optional, but basically, the identity of the question and the position of the question is the stream that comes into the encoder. And on the decoder part, we have also a few different options what to include there, but in a nutshell, it's the answers, so the correct or being correct or incorrect, and the positional encoding. And so the answers shifted are shifted one answer to the left, right? Because we can't look at the future answer, and so to prevent data leakage, all the Y truths or the true labels are shifted one to the left, and then that is forming the query that is actually asking, so to speak, the encoder, what do you have for me, given all the context that I have, tell me, what the next answer should be. So this can be thought of as like, you could come up with all kinds of analogies in the NLP world, but basically, what would my most probable next word be given all the previous context?
So let me, if I understand the position embeddings, those are actually the position of the question in a list of questions. Is that right?
No, that's the position in the sequence.
A sequence of what?
Of interaction, of the interaction.
Of the interactions.
Yeah. So the streams are interactions, and so the positional encoding encodes. So it's basically a two-dimensional tensor for just one sample, and so one dimension is the position in the sequence, like the 0th element, the first element, etc., up to whatever the maximum sequence number is one dimension, and then the second dimension is the model dimension itself. So the for example, in the bird that we saw last time, it was 768. Here, I think the D model that I was using was 128. So it's basically the dimensionality of your hidden representation that you want. So that's the other dimension. Yeah, so basically you combine the two, the identity of the question and identity of the answer, with some information about where they are in the sequence. So the positional embeddings are used to basically inject the information about relative positions of tokens, so to speak, right? And then the entire encoder, decoder, and QKV, query key value math, or the computational graph, is exactly the same as we saw in the last examples in the last session. So this is a classical QKV multi-head attention architecture. So in the end, it produces some probabilities, which is like a binary in this case, right? And then just a binary cross entropy loss is generated from comparing the probabilities with the ground truth, and that loss is, or the gradient generated by that loss is flowing down the entire structure. So that's how this models are trained. Any questions on this part?
Did you touch at all about this elapsed time embedding and lag time embedding? So we're gonna talk about them later.
Yeah. So these are peculiar to a particular paper, one of the latest research papers that they published. So they came up with this idea that not only the identity of the question or your past answers are relevant, but also how much time elapsed from this interaction and the last interaction. Maybe because if that lag is too long, maybe you forgot the topics, or if that lag is if those lags are too short, maybe it's too much of a load on you, and so in both cases you would imagine your correctness would suffer. So they included that as a parameter, and I have that too. Elapsed time, that was lag time. And the elapsed time is how much time did I take to answer my previous question. So that didn't prove to be useful in my structure, in my architecture. So I just got rid of it because it was taking space. But they found that it actually adds value. So these are both temporal features.
Yeah, and that same paper that you mentioned that has like a nice diagram that explains this lag and elapsed time.
Yes, yeah.
Thank you.
So, so final slide is about the competition itself. So these are the area under the curves. I built like a very basic. I don't even remember. I think it was like a simple neural network with a binary classification layer on top, and it was like 76, 75, 76 AUC, and if you deploy a full-blown transformer with millions of parameters and all of that, you don't get to 99 or anything. It's just slightly better. But as you can see, there's like 2% AUC difference between the leading solution and mine, and so there is quite some research and quite some work that went into this 2%. So these people deserve full kind of recognition. They actually presented their solutions at the debrief conference that they had with Riiid, and so these are links to their video presentations. This would be cool to check this out. And this was a massive competition, so more than 3,000 teams and 60,000 entries participated in that. So today we're gonna focus on the solution that I submitted, and just discuss basically the data intake and the modeling, and then the training, and then some of the engineering challenges that I mentioned.
Are those number 1 and 3, were they teams or were they individuals like yourself?
Kitar was individual. Noisy students were 2 people.
Got it.
All right, so let me actually just a few hours before we started, I tried to rerun one of the notebooks, and let me see if it finished actually, because then. No, it's still running. So okay. Anyway, yeah, just briefly about the structure. I have some of the links over here too. And you know what? Let me first just briefly go and show the Kaggle itself. So very interesting description, detailed one. They describe the data set itself in much detail, the evaluation, the timeline, and all of that. And this was what they call a time series API, the Kaggle time series API. So basically what this means is everything needs to work inside the notebook, and then you basically submit the notebook, and then the notebook is fed the out of sample evaluation test, and then basically you don't have any control, or you don't see the evaluation test, of course, and basically your notebook is being evaluated. The key requirement they had is that the notebook had to finish within 9 hours. So there were 2.5 million test examples, and 9 hours. So that gives us something like 13 milliseconds per sample, and like a few submissions of mine, for example, were timed out because that is quite a stringent requirement, and people generally they acknowledge that to be a big sort of constraint, because you could imagine you would do all kinds of ensembling, and I tried actually stacking some gradient boosted trees on top of the transformer network, and then use transformer network as a feature extractor, and maybe that would have worked if it didn't time out. It was a quite a requirement.
So,
So yeah.
if I understood correctly, you could do the training outside your Kaggle notebook, right? And you can just do inference. So the inference needs to complete in 9 hours, right?
Yeah, the inference needs to come complete in 9 hours.
Right.
Yeah. So that's what I did too. So I trained my models in Google Colab, and then you basically call it from Kaggle. You upload the model from Kaggle, and then you submit it, and then the inference has to complete in 9 hours.
I was trying to read on this API. Is the main reason they did it because they wanted to discourage people from probing the test data, or is there another reason why?
I don't know.
Yeah, because I was different in this conversation.
So that time requirement is interesting. I'm wondering, maybe you'll get into this, or maybe this question is well beyond the scope of what we're doing. But I'm wondering if anyone tried a model to try to exploit that time limit in a sense of like using simple models that could predict quickly on, say, the easy questions, and then feed the hard questions to a more complicated model that could then have more time to run those if you're not wasting the time running inference on the others. Do you know if anybody tried anything like that?
I don't remember any discussion like that, but that could be a workable approach. Yeah. So the questions, they are different in their difficulty. There are some very easy questions, and so that could work actually. Yeah, it never crossed my mind to use light and heavy. Maybe some people did. I just don't know. Yeah, and so there is tons of discussion and some great EDA notebooks, and actually the company itself suggested a few. Let me see if there are. Yeah, so for example, this one is from the company itself, and then this is from the company itself, and they provided all kinds of useful advice and feedback. So really very great competition just in terms of how the company curated the process. Yeah. So any questions on the competition before we dive into the notebook?
Yes, some of the discussion notebooks and EDA notebooks were helpful for me to get an idea of the data and what approaches other people followed.
Yep. So I have the competition here, the research paper that I mentioned, and the attention is all you need, the classical transformer paper, because these are the basic building blocks for this whole thing. So just very briefly about the hyperparameters that I used. So this was not a production ready code or anything. This was just a quick exercise for myself. So bear with me. Some of the shortcuts and the code is not very nice, but it worked, and that's all that mattered to me. So the number of questions is a number that helps us think about the embedding dimension and embedding parameters. So that's why I decided just to hard code it here and then see how it looks. So remove lectures is another flag that I use. So the original interactions themselves come with lectures, and then I tried a few options. As far as I can remember, it was 1 year ago. I tried a few options in how to integrate them into the learning, but none of them made any difference. So I decided just to remove them completely. And then, you know, I convert the lags, so the time since the last interaction into bins. So I do this, you know, continuous to categorical conversion. And the same, this is a terrible name probably, but history is basically how many interactions that student had in the past. And so these are probably equally spaced in terms of percentiles. So these are 5% quintiles probably. I'm not sure. So yeah, this is the hyperparameters. These are the hyperparameters that are used in data intake. So how you process the raw data into the data ready for data set production. And so these are a little more sort of a little more important from the machine learning standpoint. So the window is the tail that I use for each student. So how many interactions back I look to actually apply the transformer or any time series model. So this could be an LSTM parameter, right? So the number of steps in the sequence. Now this step 96 is if someone has, like, for example, 200 questions answered, do I produce 200 samples for the model to learn, or do I do some, you know, stepwise stepwise shifts and produce, for example, just 10 or maybe 2? And so this is exactly that. So I only, if I look at the history from now to the back, the next point when I look to the history is 96 points from now. And again, I don't specifically remember how I came up with this number. I think it was more like trial and error, just to see, you know, where the learning stabilizes, and it doesn't take too much time, because it could be the case that the model would have learned the best from you know, the total data set, which is, you know, each timestamp will produce a whole tail, but that would just explode the data set, and it would just not fit in memory. I'm still with these parameters. I'm on the brink. I have like 30% of the 25 gigabyte RAM only available, and so this was probably the key parameter to balance the quality of the training with the availability of the memory.
So is it like look back? Is that how many interactions back you look after 96 interactions?
Window is the look back. So window is the look back. Step is for a long sequence. You know, let me actually annotate this. So suppose, so this is your entire sequence, right? And so this is your window onto which you project, right? But then how you generate a data set from the sequence. So the step is this parameter. So this is the step. So this interaction would so this sequence will generate 3 samples, 3 training samples. So this would be number 1, number 2, and number 3. They will all have the same look back, which is this one, right? So this is the look back, but they will be generated with the step parameter. And so, you know, this thing will be basically 3 samples and 3 training examples for the data set. Okay, let me. Is that clear, George?
Yeah, I think so. So that the part you highlighted at the bottom, that's the step size, the 96.
So
And
this
people
is the window. So this is the window,
Right.
and this is the step. Yeah.
Right, got it.
Okay. All right. And so the dimensionality of the model is the length of the feature representation. So the length of the internal dimension. Number of layers is basically how many encoders, decoders we want on top of each other in the transformer. And so again, trial and error. I tried 4, I think. The most I went is 4, and then I decided to do 2. Number of heads, just a regular multi-head attention parameter. How many heads do we want to look simultaneously at the entire D model? And then if you remember the transformer architecture, there is a feed-forward layer after the attention, just basically augmenting the whatever the attention is producing and just providing additional flexibility or additional modeling capability on top of the transformer. And it has the flexibility of having a different dimension, and so typically it's a multiple of the D model itself. And then the dropout is just a regular dropout used during training, but not intrusive. So if we go into the data itself, so I already did this train Z and all of that. These are pickled files, but I already did some pre-processing back then, 1 year ago. And basically what I did is I separated some of the data into purely or mimicking out of sample validation, just trying to mimic what I would get in real life on Kaggle, and just not touch it. And so this is all except that. So this is the training itself. And if we look at the structure of the data, it's basically, it has the user ID, the timestamp, the content ID is the question ID, basically, the number of the question. Content type is question or lecture. Task container ID is a interesting thing. So in the app and in the evaluation set, the questions and lectures come in groups called containers, and then whether the question is together with other questions affects the way you basically build your inference machine, because the inference needs to understand what the immediately preceding right response was to be included in the transformer. So this is more for the evaluation. And then the user answer is 0 or yeah, this is the number of the user's answer. So there's a multiple choice, and then we don't use that information. And then answered correctly 0, 1. And so this is the labels that we're trying to predict. And then they had a few more things like prior question elapsed time, which we discussed already. And then they had also this flag, which did the prior question had explanation, because sometimes when you don't answer correctly, the app offers some explanation what you did wrong, and maybe offers some theory materials or something. And so this is a flag of whether that was the case. The idea being that maybe if they explain to you what you did wrong in the last question, your probability of being right today or right now is slightly higher. So I had a few auxiliary functions, just basically quickly built some pipeline tracking the memory all the time, and basically I processed that large data frame into something smaller, which only has user ID, the question, the true label, the timestamp, and the user total is how many questions has that user seen so far historically. So this is the tensor that we'll be working with. A quick visualization of how the history is distributed across users. We see a few people actually use that app all the time and produce, hundreds of questions. But this mode is 30. I believe it was like 30 questions is the most that people actually use. I think it was tied to the payment tier within the app. So this was the basic payment tier, 30 questions. So most of the people went just for that. Then I added another flag, which is some questions are repeating. If you didn't answer that question correctly the last time, the app would suggest you to answer one more time. So this is a flag of whether you saw this question before. Okay, and so just a quick stats. So 65%, 66% of questions are answered correctly. And so this is not a hugely imbalanced problem. There is, you would say, no class imbalance. Zeros and ones are distributed evenly almost. And then, each 8th question is a repeat question. So this is also not a very rare flag. Yeah. So as I mentioned, I had another 1 million interactions separated into a separate thing that I didn't touch. And then, we load that and we use that to mimic the out of sample validation, to mimic the out of sample evaluation at the Kaggle website. Now, there is another, technical thing that I decided to do here is basically the questions themselves, how hard the question is an important feature. And so, easy questions obviously have a higher probability of being correct. But the probability of the question being correct is changing over time. And so, it depends on basically some questions appeared just recently. They discuss it, and so we need some mechanism to track how the questions are evolving over time. So how their correctness percentage evolves over time. I have, let me not go into details, but I have a separate sort of software object built to track that. This is just a static picture of how many questions are answered correctly. And so you see that like most questions are answered correctly 80% of the times. There are a few that are probably very easy questions and are answered like almost 100% of the times. But there are a few like really difficult questions that are the probability of answering them correctly is 50% or even less, like 20%.
Do we know how many options there are for these questions? Were they all multiple choice?
No, we could probably deduce that from the answers, but I didn't use that information at all. That's an interesting question.
So I
maybe
took, I took the sample TOEFIC, and to me all the questions that were posed were 4. I always had to choose one out of 4.
Well, it's interesting that there does seem to be some questions down there that have a probability correct near 0, right? It looks like there's a little bit of area in that last bar to the left.
Yeah. So those may be the new questions on the block. So not having, any history.
Right.
But unless they have a lot of options or they have a free-form response or something, you would expect them to do better than that just by chance.
Right. Exactly. Yeah. So basically we're done with the pre-processing, and then we go into generating the data set. So the data set the key question for me to decide was whether I want to go full TensorFlow from the onset, right? So basically process just everything with the TensorFlow dataset as a generator, not to increase the memory load, etc. Or do I want to create something intermediary and then generate the intermediate and then generate the TensorFlow dataset? And I decided to go with the latter option. And so the difficulty at that point, as far as I remember, was that the traditional TensorFlow windowing functions and generally routines for working with time series, they assume homogeneous sort of stream of events, and we don't have that case here because users are different, and so the stream needs to be chopped by the users, and I just didn't find a quick way to replicate that in TensorFlow so that in each interaction, in each sequence, we only have the data from one user, and obviously we should have. So in no circumstance we could have like different users or interactions from different users within one training sequence, within one training sample. And so there is probably, I'm sure there is a TensorFlow answer to that question. How do you do that? It was just easier for me to quickly come up with something NumPy and then convert it to TensorFlow if my NumPy fit into memory. And I mean, it did with the step of 96. I squeezed it into memory, so it worked. Maybe if I found the way to do that, like in TensorFlow, I would be able to just leave the data set as it is and just apply the TensorFlow pipeline, and could have probably trained for longer and so forth. But the solution I went for was just pure NumPy. So basically, I take the entire NumPy array and then chop it off into windows pertaining to each user, and then generate the TensorFlow dataset off of that. Any questions on that? Sure.
That's an interesting approach. Yeah. Just a quick question to remind me on the feature, that QCP, is that the difficulty of the question?
Yes, yeah. Question correctness percentage. Yeah,
Perfect.
QCP is the difficulty. Yeah.
So you made a time series for each user, right? Each student.
Yeah. Yes.
Did anybody? That's what I was thinking to do too. But did anybody else try something else? Did you see anybody else that was doing differently?
I didn't dig into it.
Okay.
So the other approach is to use the user ID as a feature and let the model treat that. That's, I think most of the notebooks use that, I think.
Yeah. I just if we're thinking about the transform architecture, right? So basically, we need to feed a sequence of events into the transformer, and either your transformer needs to, the sequence needs to be really long to catch some of the answers from that same user, because only those are relevant for your current prediction, right? So answers from different users do not really tell anything about whether you're going to answer this question.
Some users, right? I mean, you might capture that here by use some kind of like average. Is it? I think might relate to that QCP. How the average response rate for that question? Is it like a hard or easy question, basically?
Yeah. So this is exactly that. So this is tracking how hard this was.
Right. So then you'd consider other users' answers in an aggregation level.
Yeah, on the aggregation level, yes, yeah. But in the sequence itself, I just want to have my own answers, right? So my own knowledge track, basically.
Got it.
There must be probably a way to do this in just in TensorFlow dataset
TF data, yeah.
functions. I just, yeah. So yeah, one we'll probably think to mention here is that Y role is the true labels shifted one to the left, and so this becomes again, this is very easy to implement in TensorFlow dataset, but if you're going pure NumPy, basically this is how I did. And so once we have that, so basically let me scroll down here. So once we have that, basically, what I do is I just go through the entire users and then chop everything, their interactions, chop into lengths of whatever my window is, and then creating another dimension for the step. So basically creating the sample dimension, which then later will become the batch dimension. So yeah, here we are. So in the end, we get a three-dimensional tensor with million something is the samples. So the 128 is the timestamps, excuse me, within each sample, and then 6 is the feature dimension. So, and to just to reiterate, the 6 features that we use is this. So the question ID, which becomes the embedding, repeat yes, no, lag, again, an embedding, the question hardness, difficulty of the question, the roles, why true, and why true is actually the label itself. So, okay. And then we're done. Not a huge thing. So in float 32, this is 4 gigabytes. So it fits nicely into the memory and lets enough space for the model to train. Let me see if we have it here. Yeah, so where is my, okay. So yeah, there was a logo to see how much memory I have.
Oh, it needs to be running, I think.
I forgot where it is. I forgot where it is. Anyway, yeah. So yeah, after all of this, we only have, yeah, this is 25 gigabyte GPU. So after all of that, we get only 40% before starting training. So this is already in the thin territory. And then basically, once we build the tensor, we apply the simplest dataset generator, which is just from tensor slices, cuts everything into along this dimension, this linear dimension, leaving this unchanged, right? So, and these are within within the same user, and that's it basically. We also
1.2 million that you have, is that a choice? Right. So basically, use the subset of the training data, right? The training data is what, 100 millions?
Yes. Yeah.
So you use like close to 1% of it.
No, actually, so this is 1.2 million windows of the length 128.
So does it cover the entire data set or part of it?
It does cover the entire data set because the entire data set enters the windows in this or that way. Some of the windows are not full windows because, as we saw, many people have just answered 30 questions, and for those we will have just one window. But for those that answered many hundreds of questions, so the windows will be generated every 96 steps. We will generate new window, and they will be overlapping. So I made it intentionally so that the step is not larger than the window size. So some questions are overlapping, but that's not a drawback. It's just a design feature.
So basically the same training record would appear multiple times? If they're overlapping, would you feed the same training record multiple times in your model?
Could you repeat the question?
So since they're overlapping, does it mean that you're feeding the same training record multiple times to your model? Or is each training record only used once, ignoring the epochs?
No, so there could be the case that some training records are used twice. For example, if your total history is, say, 200 interactions, so your 128 leading interactions will produce one sample, and then 96 steps from the zero will start a new 128, as we saw in the diagram, right? And so those will produce overlapping, so that overlapping segment will produce twice, two training samples. So
right.
So in that case where you have 200 events, if you step 96 events further out, you're not going to get a full 128 for the next window, right?
Yeah, pad with zeros. Yeah.
So you're padding with zeros.
Yes. Yeah.
So is this
everything is padded with zeros? Yeah.
Right. Is this overlapping some kind of a data augmentation or?
You know what? Yeah, I don't remember the details of my thought process at that time. I just first thought that it needs to be so there needs to be some overlap. Like you can't have 128 and then 500 elements later something. So you have to use all of the data. So that's not one. And then the frequency, that 96 or 16 or something, is dictated by the time and memory limitations rather than any clever design on my part. I mean, I would rather have it one, right? So the ideal step would be one. Just every single data point will generate its own tail of whatever the window size, like whatever lookback period is. Each leading interaction will look at the entire tail that precedes it, but that would just blow the whole thing by 100. So so 96 was probably that trial and error.
Got it.
So you're basically not using 99% of the training data that you could use due to time considerations or due to memory considerations.
So they, that's the interesting question. So I guess they are not used in the way that you think about producing the last, so the current answer, so the answer to the current question. So in that context, I have to skip like 90% of the data. But if you look at the transformer architecture as a whole, so the whole network is training. So the entire probabilities, the entire row of probabilities is compared to the entire ground truth. And so, the last element which we truly care about, is not the only one, not the only way to train. So
I see. It's a many output model that's being scored as such. So the transformer is actually training on the entire window at once.
Yes, yeah, but the training, yes. Inference,
Okay.
no. So training, yes. Inference, no. And because of this balance, I mean, all kinds of problems could arise. So I tried training a transformer so basically I tried limiting the loss only to the last element, because I knew eventually at the validation, this is how I'm going to be evaluated, and it didn't work. It produced worse results. So it's easy to do, and it was not the right thing to do.
So you're including steps then at the beginnings of the windows that really have no history, and the transformer is learning from both those and all other steps within the window.
Yes, yeah. Okay, so in the interest of time, let's get into the transformer architecture. Please tell me if I need to go deeper into any one of the component parts. I think we covered some parts of that in the last two sessions, but I'm happy to elaborate on any of these if needed. So the positional encoding is just a standard positional encoding, as I said, having two components. So the model dimension and the sequence position. So this is it. And I think, yeah, I produce here. Yeah. Anyway, and then we have pretty much the classical architecture, which is really like a copy paste from the TensorFlow tutorial. I don't remember changing anything. Maybe reshuffling or some optimization of the code, but the logic is exactly the same. So nothing has changed here. So basically, QKV, multi-head attention, looking at the encoder part independently, and then the decoder part, self-attention plus cross-attention. So cross-attention meaning, the queries come from the decoder trying to understand, which element is most appropriate here, and keys and values coming from the encoder. And so this is exactly what we saw the last time. Let me see. Yeah, the only thing that has changed here is actually the transformer itself. So the part which ingests the raw data, and I'm going to cover this in a little more detail. Yeah, so this is the transformer itself, which uses all of these layers, the encoder decoder layers as components, basically, right? And so what we have here is, we typically we have to explain two functions, so the init and the call, right? And the init is the usual init when you basically initialize this object, which are encoder and decoder objects that we just created, and then in the call you specify what they actually do, right? So basically, if you use that as a computational graph, how the data flows through the graph. So that's the call part. So the init part structures the graph, and then the call part actually tells you what to do with the data. And one thing I was going to briefly mention is the embedding. And so there has been quite some discussions and rules of thumb as to how to select the right embedding dimension. And so you probably saw the square root to cubic root to fourth degree root, if I'm using the right term. And maybe it depends on a whole lot of things. My sort of intuition or my intuitive conclusion from reading some of these research papers is that many of them are just trial and errors, more than some theoretical result. So just as a reference point, some NLP transformers, they deal with 30,000, for example, tokens, right? And the hidden dimension is 512 or 768 or 1000. And so it definitely appears that it is for this more like an advanced structures, is definitely not the fourth root. It's closer to square root. Maybe because they need more dimensionality to account or to cover possible combinations of how elements can be shuffled or positioned vis-a-vis each other. And so maybe because the space that described is just more complex. So whatever the reason is, I decided to go that way, just not to try to squeeze the model into some 16 or 64. So the number of question is 13,000, and so the embedding dimension that I use here is 258 minus some vacant depth. So some positions within that vector I leave for all kinds of things that I decided to concatenate rather than add. But yeah, I was going to make this distinction that I'm not doing the 4th degree root here. It's much more than that. Another note. So in the early papers and in some of the later ones, so the positional encoding is added, and not only the positional. For example, in the Saint paper, in the Riiid research itself, they would add the temporal encoding, the lags, and the prior question duration, etc. They would just add to the question encoding, and there might be good reasons to do that. If that works empirically, that's great. It just it seemed to me I wanted to try concatenation specifically in this example because the concatenating features are not like big features. Like some of them are just binary 0-1s, and then if we can afford concatenating and just letting the model learn itself from the raw features, my idea was that probably would be better than adding to something else and forcing the model to deduce complex relationships between the two. So that was my sort of thought process behind concatenating rather than adding. And I actually tried adding, and it was slightly worse. So I thought this was a nice sort of nice finding, at least in the context of this small exercise. So yeah, and then basically we ingest the the data set or the batch that we just prepared from the previous data pipeline, and push it through the transformer and produce the final sigmoid output. So that's the final layer that is produced. One thing, final thing to mention here, I was going to mention, is that so in this example, in the previous transformers that we discussed, encoder is usually fully transparent. So the encoder looks at all of the content in both ways, and the decoder is strictly generative, right? So the triangular mask that cannot look into the future, but can only look in the past. So that's the classical architecture. In this case, I thought that it would be more appropriate to have them both be triangular. So both the encoder part and the decoder part can only look at the previous questions and the previous answers or rolled answers, and not peek into the future. Like, for example, the fully transparent encoder mask would mean that somehow my question today can look at what I'm going to answer, or what questions I'm going to try, tomorrow, which, didn't make much sense. So I decided to apply, triangular generative masks for both the encoder and the decoder. Let me pause right there and see if there are any questions on this part.
Did you start with that, or did you try the transparent one, and then you went with a triangular mask?
I don't remember the evolution, but I think I tried I didn't try the fully transparent. I started with triangular, and I kept triangular.
And I was
think so.
trying, right, and I was trying to find your code. Where do you concatenate the different?
This is the, let me see.
Instead of adding them, the different embeddings.
Yeah, so this is the concatenation. Yeah. So I concatenate the embedded question, the lag, and so this this one-dimensional features. Yeah. So this is the concatenation itself.
Right. Okay. Thank you.
And axis is 2 because the 0th axis is the batch, and the first axis is the sequence, right? So we concatenate it along the feature dimension, the last dimension. Yeah, and so basically, after that, there is a big section that deals with mimicking the evaluation, and some parts of this came from other notebooks. And again, if you're interested, you could check them out. Great notebooks, saved tons of time because I just used the ready classes. No need to create anything on my own. And as I said, I had to create a few classes that keep track of the history, because in training everything is transparent. So you have all your history for a particular user there. So basically there is nothing to deduce. But in the evaluation, because it's a 2 million, 2.5 million evaluation set. So, and they say explicitly that some of the users are new, will be new. You don't have even the user ID for them. And so there needs to be some object sitting in memory in Kaggle that in the Kaggle notebook that keeps track of the the user specific history of the answers and whether they were wrong or right, etc., to build the tensors to feed the transformer. And so quite some work went here, which is not data science, not transformer specific, but unfortunately that was the only way to participate. And then let me get straight to the training part, which is I think the most interesting. So a few hyperparameters. So I only trained, I tried retraining this again. My Kaggle submission was trained for 20 epochs, if I'm not mistaken. But basically, because I used gradient tape here, again, following the TensorFlow notebook, TensorFlow tutorial notebook, I use gradient tape, and that gives you flexibility to do whatever you want on the batch granularity. So basically, after each batch, after pushing each batch through the transformer through backpropagation, basically, right? So after updating the weights, you can do anything. You can do nothing, or you can perform any action, like do some reports, do some validation, etc., etc. And so this gradient tape gives you great flexibility to choose when you want to do what. And because this is a massive data set, this was very useful. And so just every 500 batches, I produce a small report. Every 5,000 batches, I do a validation. And then every epoch, I do out of sample validation, just using my 1 million. I do just mimicking the Kaggle evaluation. And then every epoch I do checkpoints. So David, I remember the questions we had last time on the gradient tape, and you asked about this context manager that they used. So this is the link to that page, but basically this is how they explain it. They don't explain why the context manager works the way it works, but generally basically it's an object that keeps track of the gradient, and then is used to sort of apply those gradients to the optimizer, and they have a very specific syntax we need to follow. And yeah, so this is exactly what we saw last time. So basically, just a quick comment. Again, the same TF function decorator that we saw last time. So allowing TensorFlow to build the computational graph in memory and train it much faster compared to without these decorators. So if you're building something big, it's a good idea to have this decorator just to let TensorFlow know what is the shape of the tensors will be coming in. And then yes, so this is the elementary training step that takes a batch and produces, basically updates the updates the gradients through this syntax. So optimizers apply gradients, and then the gradients that we just calculated with your variables. So this object holds elementary unit gradients for each of these guys, for each of the trainable variables. And then this is an example of how it works. So basically, training consists of 2 cycles, right? So the epoch, and then within the epoch is the this thing. So within the epoch, we go through each training example. I don't think there is a way to avoid these for loops. So to vectorize it somehow, it is just it has to be linear. And then so basically within each elementary step, within each training batch, basically we can check if the reporting frequency has come, or the validation frequency, or out of sample validation frequency, or we should checkpoint, etc., etc. And you can produce any kind of visibility that you need. So this particular notebook ran for 3 hours, I believe. Something like 3 hours, yeah. 5 epochs in 3 hours. And this is the validation, out of sample validation, and yeah. So I'm just running through the notebook to focus on one part that I like the most here, which is the permutation feature importance. And it gives you, it basically compares the true AUC that we produced using the true model with AUC that we get from scrambling some of the features. And so that gives us an understanding of the relative importance of the features, right? Which features produce the most damage after scrambling them, after randomly shuffling them. And so you can see that question ID is dominating by far, right? So if the transformer doesn't know which question you're answering, it can produce a good probability. But it's not that it's completely blind, right? So the AUC was around 80, and so we take away 20, but still 60% AUC, even if we don't know which question you're answering. Y roll, so basically the previous label is very important, and it's basically you're answering history, how right you were in specific steps in the past is very important. And then the difficulty of the question is quite important. The repeat and the lag are basically roughly the same magnitude. Yeah, so that's in brief. I think it's 8:25, so perfect time. Please go ahead with questions.
Yeah, thank you, Dmitri. This is really useful. So the way that you calculated this permutation, you did inference on the model without that feature, and you saw what loss your model incurred. Is that like at a high level?
High level, yes. So it's not without that feature because it's technically would be difficult to remove the feature.
Right.
Like if we were to remove from the dimension, we just, instead of removing, we do a simpler thing. We just randomly shuffle the feature. And then we infer on the randomly shuffled test data set, and we see what the metric is. And then if the feature was important for your metric, shuffling will produce the most damage. If the feature was not important, your metric may not care at all.
So when you say shuffling, where are you shuffling? Are you shuffling the columns or the rows, or what do you mean by shuffling?
I shuffle the so let's say you have like a two-dimensional, for simplicity, two-dimensional table, right? And you build a model that, so the two-dimensional being features and samples,
Mhm.
and then you take the same test data set and you shuffle the column, you shuffle the feature column, and so basically you produce a random permutation of the column, leaving everything else as is, and then you predict on the shuffled data set, and you compare to your ground truth.
So you actually you impute new values, random values, or you just change the position of the feature where it is in your model? In your
no. So we shuffle the values. So if this is my data, right?
Mhm.
So this is the samples, and this is the features.
Right.
This is the test data. The model is already trained. We don't touch the trained model, right? So, and we want to test how important this feature for the inference, right? So we take this feature, we leave everything intact, but we shuffle the contents of the feature. So basically, 1, 2, 3 becomes 3, 1, 2.
Right.
Everything else stays as is, and then we take our model and then we predict on this shuffled thing, and we get some some new y's which are shuffled. And then yeah, so that's and you could do, if you have time, and if the capacity allows, you could do several rounds of shuffling. And so for the light models, and I guess we saw some of that in the past in deep learning adventures. So for the light models, you could do several rounds, and then instead of just one, you would produce something like this is the range that your metric will deteriorate. It's a little more specific.
Yeah, so it's usually do a lot of, as you say, a lot of rounds to get a better, more accurate value. And the great thing about permutation importance is you're doing it on the set that you're interested in. So you wouldn't necessarily do it on your training. You might do it on your validation, or if you're evaluating something where you have a test set and that you held out, that you know the answers for. You're evaluating the permutation importance for that actual predicted set. So whereas like other types of feature importance that you get from like trees and things, they're done against the training data. This is actually looking at the predicted data, right? The like for your validation set or your test set that you held out. So you get a real, it's a better look at how the features are important for the predictions that you're ultimately going to use it for, not necessarily just the training, right?
Yeah, this feature importance was covered in that Kaggle model explainability course
Right.
as well. One of its limitations is that if you have correlated features, it can give you somewhat questionable results, right? You can imagine that if you have highly correlated features, suppose you have two features that either one of them explains the model very well, it might show that the feature importance for both of them is small, because if you shuffle one of them, you still have the other one. Whereas then maybe some other feature that isn't that important can come out looking stronger than it is.
So then
Yeah,
you do
that's
shuffle
what's
like
going on.
pairs of features or tuples
Yeah,
of.
one other cool thing about this is, it could work for any model, right? Some other feature importances work for specific types of models.
That's right.
Yeah, and this is like, completely black box thing, and still produces some interpretable results. So, yeah. We can go.
Yeah, another advantage of being something that only depends on the test set.
So yeah, the transformer itself only had 3 million parameters, I believe. Let me look. 6 million parameters. Yeah, but this is still not like a huge model. And I thought maybe if we had more time, if I had more time or compute, etc. So this would be another direction I would try, because it appears that in the transformer world, the size continues to matter for some time at least. And so I would be very interested to see what happens if we deploy like 60 million or something, which may or may not have an effect, but this is certainly a direction. And because the data set is growing, something tells me that they might revisit this challenge, because they actually advertised this Kaggle competition as a great achievement, because so many people participated, and apparently the winning solution improved their own AUC, so their own internal performance. And so this might be a repeat competition, so let's keep an eye on that.
So Dmitri, after you trained this model and got this result, did you save the model out and then import it into Kaggle to run in your notebook there?
Yeah.
Or
Yeah.
Okay. And is it one of those where you could just do that directly, or did you have to like create some data set to pull the model?
Yeah. So yeah, the data set, yeah.
Okay.
Create a data set, yeah.
Because if I understood correctly, when you submit it, right, the entire notebook needs to be submitted, so you can't really do an upload function there.
No, it has to upload from the data set, and
Right.
then you just, yeah.
It needs to be
I think once you click submit, you just can't even go and see what it's doing. It just, goes completely blank. And then, 6 hours later, it tells you, something went wrong.
Right.
Noticing.
Yeah. So this is like a cleaner version of the work. In this is basically the end result. But I had the modules that tracked inference time, and as I said, it was not easy to squeeze the inference into this 13 milliseconds. So it's been from an engineering point of view, for myself, it was quite a challenging competition.
Yeah, this is a great solution. How many hours would you say you spent to get to this point?
It's it's difficult to estimate. So I made 20 submissions, from which 5 went timed out. So I guess I would spend a couple of hours a day probably for about a month.
Okay.
So that's, yeah, roughly.
And as with any good Kaggle competition, people are leaking out things and you're using that in your notebooks and stuff like that. But did you find that really helpful to keep in the discussions or looking at other notebooks during words or after?
So yes, because first of all, the Riiid people themselves, they commented on the questions, and
Okay.
I found their comments very useful. So some competitions, from what I can tell from discussions, the companies, the sponsors, are not that active, and they basically put out the competition and they don't care, probably. I don't know, but these folks were very much engaged. And secondly, this software components and the ways to make sure your evaluation works correctly, etc. So the classes, the ready classes, etc. As I said, I just basically forked without changing anything almost, and so it was a very helpful group of people. Yeah.
Very cool.
I like that you had to develop your own submission environment to emulate what Kaggle would do, so you don't have to wait.
Yeah. This was the I guess in terms of how many errors I saw, this was probably the most buggy and error prone piece of the code, because so many pieces have to work correctly at the same time. As I said, you keep track of everything in a blind sort of folded fashion, because you don't have access to that, right? And so new users, old users, repeat questions, and all kind of things can happen in the evaluation test set, and all of these scenarios can basically break your code. So.
Right. This out of sample, is that at a high level, is that the same data set, or is it like a different data set every time you call it?
So this is the same data set. It just the data set which I separated and kept in the original format as if it were to come from the the Kaggle evaluation engine. So the entire pre-processing pipeline and whatever the data set, etc., we can't do on the out of sample evaluation. So the out of sample is just the raw 1 million rows or 2.5 million rows, whatever. They tell you which format they will, you should expect. And so basically what you're trying to do is, let me separate that myself and then try to see what should I have in the notebook to process that raw data into the format that we need to produce predictions. This is as opposed to the typical regular validation which we had, which is basically randomly splitting train and validation just for the purposes of keeping track of the training dynamics. So that's a separate thing. And the OOS validation was pretty slow. That's why in the setup. So I can only afford out of sample validation once an epoch, and this regular validation, it was basically cheap. I think it was like maybe a few dozens of seconds or something, but it was not 10 seconds for in-sample validation, but the out-of-sample validation took you 700 seconds just to produce what you should expect from the Kaggle notebooks.
Noticed you logging a lot of things. Did you use TensorBoard to display any of this?
Yes, I used TensorBoard. There was a separate object that pushes stuff to TensorBoard during the cycle. I don't even remember where specifically, which training objects went where. So, so let me not demonstrate that, because TensorBoard is a buggy creature, as you know. Right?
I didn't have the best experience with TensorBoard and Colab, that's why I'm saying. One more question: when you started this research, did you try like simpler models and then you came with this same inspired model? Right.
Yeah. So as I said, I did just a quick baselining just to see what is possible, and so just a simple binary classifier that didn't have the temporal dimension. Just basically, which question, which user, and a few binary things. So that could already produce a probability, right? And as I said, the AUC was 75, 76.
Awesome. Thank you, Dmitri. Any more questions for Dmitri?
Okay, let me stop sharing then.
Thank you, Dmitri. This was very detailed, and thank you for sharing your notebook. We'll took a look already, but yeah, that's great resource for us to reference to.
Yeah, great presentation. Thanks, Dmitri.
Thanks, Robert. So in terms of the transformer structures, if you guys are interested, so the presentation by the number 1 was very interesting, like really interesting what he did. He basically put a RNN on top of a transformer structure. So transformer was extracting the features, and then there is additionally an LSTM on top of that. And number 3, this noisy students, was also a very interesting presentation. So people used GPU clusters like 16 or something. So serious work.
Yeah, all those, both of them are recorded. Yeah, we can take a look at them. Cool. Let me quickly share my screen and wrap things up. Yeah, this is me trying a very basic approach here with like a tree-based model. And I know this takes forever to score. I'm like 73 in private. This is the paper from the number 1 the winner of the competition, like you mentioned, it is transformer based on LSTM on top of it. He doesn't explain in detail all the things that he tried. It's like a 2-page paper he wrote. He just mentioned something about lowering the complexity of this. He talks about this time complexity when he only looks, I think, at the last question. Then there's 2 same papers, right? The original same paper and the same class. That's what I realized. And this is just a diagram of the different features, right? So when you take an exercise and response, the time between them is that elapsed time. And then you might take a break from one response before you start the next exercise, and that's the lag time. And these are the features that we also used. Then you mentioned the first and third place recordings are up there. Give your GitHub, which we have on the page as well here, and then several resources for this. I just wanted to share like quickly just some sample questions. So in another data set, that questions.csv, there's a part number, which basically identifies which out of 7 parts you are. And the first 4 are like listening related, and the other 1 are like reading related. And I think the last one was the most complicated to me. But you have an idea of, you listen to something.
Number 1. Look at the picture marked number 1 in your test book. A.
He's shoveling some soil.
B.
He's moving a wheelbarrow.
C.
He's cutting some grass.
D.
He's planting a tree.
Right, so you listen, you're presented with an image, right? And you're given options, and you're supposed to select one that is right. And some other ones were more like text heavy. So maybe there was a text and there was like a comprehension of what was happening. There were other ones where you had to fill in the blanks. I don't know which part that was, maybe 6 or 2 or 3. But you can see like the difficulty is different for, yeah, this was like fill in the blanks. This one was, what was this? Pure listening. So you just listen to the conversation and you give the answer.
Number 7.
Where's the new fax machine?
A. Next to the water fountain. B. I'll send a fax tomorrow. C. By Wednesday.
So these are the easy ones, but remember there were some even tricky ones where the answers were really close to each other, you know, like really similar.
So is that a listening comprehension question, or is it referring to some previous? Because it seemed like there was only one answer there that made sense, even regardless of some previous. Yeah.
Listening comprehension, yeah. So 1 to 4 are photograph, question, response, conversation, talks. 5, 6, 7 are incomplete sentences, text completion, multiple passages. Yeah. Yeah, I had to take so to apply for grad school in the US, we had to take something called TOEFL, Teaching of English as a Foreign Language. This is teaching of English for like more like a workplace environment. So you get a lot of like, how do you use English in a workplace environment versus in general in an academic environment. That's the difference. Cool. Thanks again, Dmitri. A very interesting session. Appreciated all the effort that you went through and sharing it with us. So we have a couple more sessions coming up, friends. We're going to, as I mentioned in the beginning, change gears. We're going to talk a little bit about AWS certificates. We're going to start with an entry-level one, and then we're going to talk about the machine learning one after that. Then we're going to take a break for Christmas, New Year, and then we're going to come back in January. Cool. That's it. I'm going to stop the recording here. Thanks everyone for joining us. And again, thanks, Dmitri, and thanks everyone for your great questions.